Here are the solutions to the two problems I assigned with looking now at examples where each slice is a washer. So for numbers 5 and 8, which is what I assigned, 4 pi over 15 cubic units and 2 pi over 35 cubic units. So you can pause the video now, check your work. I have the solutions explained on the next couple pages. All right, for number 5, we had to go back to the two curves from number 4. Off of GIF 7.3, we wanted to find the volume generated by rotating the region described in exercise 4 above about the y-axis. So we're switching how we're rotating it. So first of all, our graph looks like this. So just again, we have to look at the curve here for x cubed plus 1, and then we have our line x plus 1. But now we're taking this and we're revolving it about the y-axis. So we get our circles that tend to look like this. But then we have something in the middle too to try to draw this, so we're getting a washer because that middle part is a hole that's right there. So kind of drawing it down here as well. And then we have something in the middle, so that might help you see that we're getting, again, a washer. So to find this area right here, we just take the area of the outside circle minus the area of the inside circle. So that's what we want to kind of break down into parts. First, I need to recognize what is the length of the radius that reaches the outside, and then what is the length of the radius that reaches the inside. So looking at, let me go with red here. Looking at this part, I want to go to the outside, the outer radius first. So because this is about the y-axis, we need to rearrange these expressions. We need to integrate with respect to y. So this y equals x cubed plus 1, I solve for x. I'm going to get a y minus 1, and then I take the cubed root of it. So x is going to equal the cubed root of y minus 1. And then the above curve is just going to be x equals y minus 1. So those are the two expressions I need to substitute in. So my outer radius is really the x value I reach, and x is equal to the cubed root of y minus 1. So that is the length of my outside radius, the longer radius. And then the length of the inner radius or inside radius is just going from the axis of rotation here over to the left, or the leftmost curve that we're looking at. So that's x is equal to y minus 1. So the inside radius is just y minus 1. Now we're going to take a look at how do we express the area of the outside circle. Well, that's just pi r squared. So it's pi times this radius up here squared. And then the area of the inside is pi times the innermost radius, or the radius of the inner circle, so pi times the quantity y minus 1 squared. So now the volume, again, we're going with respect to y, so we're going from 1 to 2 here. So our volume is, I just put the pi on the outside because it is the area of the outside minus the area of the inside, so I just stuck the pi out in front. Again, y is equal to 1 to 2, and then very carefully writing it out this way. Now keep in mind we can't write it any other way. And based on what we're looking at here, we actually end up using u substitution. So I'm going to let u equal y minus 1. du over dy is equal to 1, so du is equal to dy. Now I left everything in terms of y. I didn't change the limits of integration here, but I went ahead and found the antiderivative here. So again, this will become u to the 5/3 over 5/3, which means I just multiply by the reciprocal here, and then minus u cubed over 3. Again, I'm leaving it y equals 1 to y equals 2. Then I want to bring back in the y minus 1 here. Very easy to say, well, 2 minus 1 is just 1. 1 to any power is 1, so I just get 3/5 minus, this will just give me 1/3. Substituting in a 1 here, I'm just going to get zeros here, so that's just minus a 0. Common denominators, final answer is 4 pi over 15 cubic units. Okay, looking at number 8, we're back to rotating about the x-axis. Now very carefully, these are both very close looking curves, so we want to be very careful when we go to graph this. So if you notice, what I have in green is y equals x squared, and what I chose because they both intersected x equals 0 and x equals 1, so I chose that x equals 1/2. So I know when I square a 1/2, I get a 1/4. So based on how I numbered here, I'm just going up a fourth of the way. But then if I took 1/2 and I cubed it, I get 1/8. So the y equals x cubed actually sits below in the first quadrant here, y equals x squared. So you know that any number squared, especially when we're looking at fractions, is going to be greater than a fraction that's cubed. So I am rotating this about the x-axis. So here is how I'm getting the washers. If I were to take my slice here, and again, very narrow washer that we're looking at, or even over here, a little bit easier to tell, and then we get the inner part that's right here. So again, looking at my outer radius, I go to the curve that's up top. So my outer radius is just going to be x squared. My inner radius is where I'm going to go to the y equals x cubed. So my inside radius is x cubed. My outer area is pi times x squared squared, and then my inside area is going to be pi times x cubed squared. So this makes it really nice, very easy expressions here. So my volume, again, with respect to x, I'm going just from 0 to 1, so I have the pi on the outside, x to the 4th minus x to the 6th dx. No need for u substitution here, just take the antiderivative. Substituting in the 1, we get 1/5 minus 1/7 minus 0. Common denominators here, and we end up with 2 pi over 35 cubic units. All right, so I hope you guys have had the time to really look at these examples. Again, please write these down. Even if you had to look at these answers as you were working them out, that is perfectly fine. Like I said, I just want you guys to get a general understanding of this. I'll give you short quizzes by the end of the week, Thursday or Friday. We have 1 or 2 more sections just to look at it. And again, I'm just going to give you a couple problems for each lesson. As always, take care. Let me know if you guys have any questions on these.